everyone, this is my introduction video and I will discuss all the reaction mechanisms in the organic chemistry. And if you see in organic chemistry, there are several types of organic reaction. First one is substitution reaction. Second is elimination. Third is addition reaction. Fourth is radical reaction. And at the last we have oxidation reduction reaction. So I will discuss the all the mechanisms of substitution reaction, elimination reaction, addition reaction. These are the major part of the organic reaction. So before you start the substitution, elimination and addition reaction mechanism, there is very much useful things, that is general organic chemistry. This is very important part of every mechanism. So I will discuss some of the general organic chemistry that is related to substitution reaction mechanism, elimination reaction mechanism and addition reaction mechanism. So it would be helpful for showing up, discussing up all these mechanism. Let us start with some under this GOC. I will discuss the basicity and nucleophilicity and some of the examples of these two. And third, correlation among basicity and among nucleophilicity and basicity. Okay, let's first start with basicity. What is basicity? We know what is base. Let's say basicity. So first of all, we should know what is base. A base is a anion. All the anions are the base and lone pair carrying compound. Okay, so base is the anions or lone pair carrying compound. So if we go to term basicity is the ability to donate its electron. So greater the ability of base to donate electron, greater is the basicity. So I will discuss some of the rules to decide the basic order. Let's say first one is anions are the good base. Anion are the good base, then its parental molecules. So anions are the good base, then its parental molecule. So also we can write that cations are the least base, then its parental molecule. Okay, let's take an example, it will be more clear. Let's say we have water and the corresponding anion will be OH minus, corresponding cation will be H3O plus. So we have these three. This is the parental molecule, this is the anion corresponding to this, and this is the cation corresponding to this. So this line says anions are the good base, then its parental molecule. So OH is the good base then H2O, and cations are the least base then parental molecule. So cation are the least base. So if we see in general that this has the lone pair density, this has charge density here correspond to this one. This is the deficient in electron, this is rich in electron. So this is rich in electron, so this has the richer electron density, so it can provide to others. So this is the more basic than this one. Let us now come to the periodic table. If we see in the periodic table from the left to right and from the top to bottom, if we see we can see that from left to right there is the increment decrement of the basicity. Let's see here in the periodic table left to right. If we see an example, let's say we have CH3 minus, NH2 minus, and we have OH minus and F minus. As we are going from left to right in the periodic table, there is the increment in the electronegativity. We all know what is electronegativity. It is the tendency of an atom to attract the negatively electron. So we have a fluorine and we have a CH3 minus. So electronegativity of fluorine is higher. So it has greater tendency of attraction of negatively charged electron than CH3 minus. So as the electronegativity increases, we have to decide the basicity on this electronegativity. So we can say that it has higher electronegativity, so it has lesser tendency of donating the electron, because it has higher tendency of attracting the electron, so it would have the lower tendency to donate its electron to others. So in case if we see the CH3 minus, this has lower electronegativity, so this would have higher tendency to donate its electron to others. So we have compared these two. This has higher basicity than this, because of this has lower electronegativity compared to F minus. So we have basicity in this order. So basicity here is inversely proportional to electronegativity. Okay. In the next point, in the periodic table top to bottom, if we see in the top to bottom, let's say we have F minus, Cl minus, Br minus and I minus. What we can see here, the size is increasing here. Why the size is increasing? As you go from top to bottom, there is a addition of one extra cell down to the group. So as the cell is increasing, cell number is increasing, size also increasing. So as the size is increases, there will be decrement in the electronegativity. So electronegativity will be increasing from bottom to top. So electronegativity. Okay. But if we see the basicity here will be lesser, and basicity here will be higher, because it has higher charge density. Because if we see that from the bottom to top, the size is decreasing from bottom to top. So as the size is decreasing, there would have higher charge density compared to I minus. So F minus has higher charge density than Cl minus, Cl minus has higher charge density than Br minus, and Br minus has higher charge density than I minus. So as this has higher charge density, it has greater ability to donate to others. So So likewise Cl minus would have greater tendency of giving electron to others in compared to Br minus. So basicity will be in this order. So here basicity is basicity directly proportional to electronegativity. Okay, so let me repeat it again. In the periodic table you can see that electronegativity is increasing from left to right. Why electronegativity is increasing? As you can see that they have the same cell number, but the proton number is increasing, so there is a tendency of attracting the negative charge electron increasing. So electronegativity increasing. As electronegativity increasing, there is a decreasing tendency of donating electron. So basicity decrease in this order. So increase in this order. So basicity is here inversely proportional to electronegativity. In the periodic table from top to bottom, we can see size is increasing as the cell number increases. So electronegativity will increasing in this order. Though it has higher electronegativity, but it has higher charge density also. So in greater availability of electron for fluorine air in compared to Cl. So Cl has greater availability of electron than Br. Br also have higher electron density than I minus. So they have greater tendency than Cl. Cl has greater tendency than Br. Br has greater tendency of giving electron than I minus. So we have basicity in this order increasing. So basicity is directly proportional to electronegativity here. Okay, let's come to the another aspect of deciding basicity, that is negative charge density is more, negative charge density is more is the basic strength. If the negative charge density is more on an element, then it has greater basic strength. Let's say if we have N3 minus, O2 minus and F minus. So here we can see that charge density on nitrogen is greater than charge density on oxygen. Charge density on oxygen is greater than charge density on fluorine. So we can write that there is a greater availability of electron to donates than oxygen. Then oxygen has greater electron density to donate compared to fluorine. So we have the basicity order in this way. Okay. The next point is, as steric hindrance around negative charge increases, basicity increases. Let us see how. We all know what is steric hindrance. So as the steric hindrance around negative charge increases, basicity also increases with that. Let's take example. It will be clear that if we have O minus and it is connected with 3 methyl group. So the second we have 1 hydrogen, 2 methyl group, and the last we have minus 2 hydrogen, 1 methyl. Okay. If you compare the basicity here, what you can see, there is a steric hindrance here. Then so the basicity will be greater here. As the steric means there is a bulkier group CH3 and this is giving the giving its electron. They have plus R. Methyl shows plus R effect, so they will give electron while increasing the electron density here. So electron density will be more here in compared to here. because here there are two donating group here, but here there is 3 donating group, so there will be definitely charge density more than this. So if we compare between these two, there is 1 donating group and here is 2 donating group. 2 donating group will donate electron, so there will be definitely a charge density that is more in compared to here. So as the charge density is more here compared to here compared to here, so we will have the basicity in this order. Okay, so that is what the point is saying. The steric hindrance around negative charge increases basicity. Okay, the last point I will add, that is, this is also another aspect of deciding basicity, that is non-metallic oxides with lowest oxidation state is basic one, more basic. Non-metallic oxide with lowest oxidation state is the basic one. Let's say we have NH3 and N2H4. So if we see the structure here, you can see that this has H. So -3 oxidation state, because there will be positive charge here, positive. So 3 minus will come here, and there will be N2H4. So positive charge, negative charge, positive charge, negative, -2. So what it is saying, that non-metallic oxide with lowest oxidation state is the basic one. So lowest one is this one. So N3 minus will be greater basic than N2 minus. Okay, I hope you have understand this. Now I will discuss the nucleophilicity correlation with basicity. So how the nucleophilicity depends on basicity. Nucleophilicity depends on basicity. We'll see the nucleophilicity across the periodic table as well as from top to bottom in the periodic table. For this, I will go back to the periodic table point that was here. In the periodic table, from left to right, we have the basicity here. Basicity was decreasing in this way, it was increasing in this manner. So if we see the nucleophilicity here, this has the higher nucleophilicity because it can give to others easily. So here basicity will be directly proportional to nucleophilicity. Okay, but in the case of periodic table from top to right, the basicity is here. I should not write like this way. It will be nucleophilicity is directly proportional to basicity. Okay, nucleophilicity is depending on basicity. Okay, if we see in the periodic table from top to bottom, what you can see that nucleophilicity is inversely proportional to basicity. So these are the two cases you should remember, that from left to right, nucleophilicity directly proportional to basicity, and in the periodic table from top to bottom, nucleophilicity is inversely proportional to basicity. So if we write in the first periodic table left to right, nucleophilic order will be CH3 minus greater than, there will be NH2 minus, OH minus and F minus. So nucleophilic order will be like this way, and also basic order will be like this. But in the but if we see from top to bottom, let's write here periodic table, top to bottom, say fluorine, chlorine, bromine, iodine. So basicity is in this order. Nucleophilicity will be in the opposite order. Nucleophilicity. Why it is happening like this way? We have fluorine and iodine. Fluorine has the higher electronegativity in the periodic table. Fluorine is the most electronegative, so it will not give its electron. It will not donate. It has electron density, but it will not donate to others because of its higher electronegativity. So it is a poor donator. So nucleophilicity will be like this order. Okay. The next point, if nucleophilic site are same, then nucleophilicity directly proportional to basicity. Okay. If nucleophile site are same, nucleophilicity is directly proportional to basicity. Let's take an example and see what is happening. Let's say we have RO minus, we have OH minus, and so HO minus, we have C6H5O minus, and we have RCOO minus. Okay, we have these four. If we notice here that this is a part of alcohol, this is a part of water, this is ROH, this is water, this is part of phenol, and this is a part of carboxylic acid, RCOOH. We know that acetic acid is the most acidic. Then comes the phenol, that is more acidic than water, and water is the more acidic than all the alcohol except methanol. So H2O is more acidic than alcohol except methanol. Another point I will write here, that is stronger acid gives weaker conjugate base. So these are all acids, and acid have the conjugate base. These are all conjugate base. So we have the highest acidic, this one acetic acid. So the conjugate base of this highest acidic one is the lowest basic, and so the acidic order will be acidic order of acid will be RCOOH, C6H5OH, and we have water, then we have ROH. Okay, so we have the conjugate base of these acids, so the basic order will be the reverse way. Let's say we have conjugate base O minus, C6H5 O minus, OH minus, and RO minus. So this was the acid and this is the conjugate base. So conjugate base has of higher acidic will be the lower base, so it will be in this order. Okay, so the basicity will be here in this order. So as we have seen that basicity, nucleophilicity is directly proportional to basicity. So nucleophilicity also will be in this order. Okay, RO minus, HO minus, C6H5 O minus, CO minus. Okay, I hope you have understood this. We also have another three points to decide the nucleophilicity. Let's see what are those. Let's say another point. Next point is bases are good nucleophile than its conjugate base. Bases are good nucleophile than its conjugate acid. Whatever we have seen earlier, we have said that cations of the parental molecule is the least basic, and the anions of the parental molecule is the higher basic. So bases are good nucleophile then its conjugate acid. Let's say we have H2O and OH minus. OH minus are base and its conjugate acid is the H2O. So OH minus has greater basicity. So OH minus has greater basicity, so nucleophilicity also will be greater. Nucleophilicity is directly proportional to basicity here. Okay, let's see the next point, that is as steric hindrance increases, decrease. As steric hindrance increases, nucleophilicity decreases. How? Earlier we have seen that as steric hindrance increases, the basicity increases. But as basicity increases, that doesn't mean that nucleophilicity also increases with basicity. Nucleophilicity here is inversely proportional to basicity. How? Let's see. Let's say we have CO minus. The last example we have taken same as this. We have CH3, one hydrogen, O minus, and we have one CH3 and O minus. Now see, we have seen earlier that basicity is greater here because of electron density here is more compared to here. Electron density here is more compared to here. The basicity is in this order. But the nucleophilicity, in case of nucleophilicity, if we see that this has electron density, but it cannot give its electron because of this bulky group. Whenever a incoming group is coming to take this electron, they will hinder those incoming group. So they will prevent the incoming group to take this electron because they are bulky group. So we can see here there is 3 bulkier group that will be preventing the incoming group to take electron from oxygen. So here there is number is decreasing here to bulkier group, so there will be somewhat easier for incoming group to take electron. In case of this one, incoming group will easily take the electron from here in compared to here, because there are one bulky group. Here there is one bulky group. In the last case, if we take this O minus and we have 3 hydrogen attaching with it, so this one can easily give its electron. So the nucleophilicity here will be in this order, but the basicity was in the reverse way we have seen earlier. So here basicity is inversely proportional to nucleophilicity is inversely proportional to basicity. So in the two cases we have seen, for this case and earlier we have seen in the periodic table, when we are coming from top to bottom, the nucleophilicity also inversely proportional to basicity. Let's come to next point. Let's say we have two group O minus and HO minus. So if we want to conclude the nucleophilicity order, then the nucleophilicity order will be more for this one, because this is the lone pair. So lone pair will be donating its electron to here. So this lone pair is increasing the electron density on O minus. Here there is no lone pair group, so there is no one to increase the negativity, increase the charge density here. So here is the charge density, greater charge density, so greater is the donating ability. So nucleophilicity will be in this order. So we can write a comment that if nucleophilic site is bonded with such atom which contains lone pair electron, then its nucleophilicity will be greater. Okay, I hope you have understand this. So let us come to the solvent effects of what are the types of solvent. For a reaction mechanism, we should know the types of solvent we are using. So if we talk about solvent, let's say we have solvent is of two types. One is polar and another is non-polar. So polar is always with high dipole moment, non-polar is lesser dipole, it has lesser dipole moment. Okay, if you see the polar one, polar also has two types, polar protic and polar aprotic. Let us now see the nucleophilicity in the solvent. Nucleophilicity in the polar protic solvent, polar aprotic solvent and non-polar solvent. Let's now see. So we have polar protic, we have polar aprotic, and we have nonpolar. So we have three solvent. If I discuss some features of polar protic, let me write here. It solvate enhance. So polar protic solvent only enhance. Do not solvent. Do not solvate cations. So one feature is the main feature is, of the polar protic is it only solvate the anions. It do not solvate the cations. So if you see the nucleophilicity order for this, let's say we have F minus, Cl minus, Br minus, I minus. So it will solvate the anions. It is coming, let's say F minus is coming from Fs, it is coming from HCl, HBr, HI. So let's call HF. So polar protic solvent do not solvate the cations. It will not solvate the H. It will solvate F minus, Cl minus, Br minus, I minus. So we have to see here the in which case, in which of the element there will be more solvation. So F minus has the greater charge density. So charge density is in the order charge density, because F minus has the lower size. So lower size, greater charge density. So as the charge density is more, there will be more solvation. So solvation. So here there will be more solvation in compared to Cl minus. Cl minus will have charge density more than Br minus, so more solvation of Cl minus than Br minus. As well as for this two also, Br minus will be more solvated. So as there is more solvation, there will be more number of ions will be attached with F minus. Ions in the sense F is solvating. So we have polar protic means there will be hydrogen. Let's say polar protic hydrogen is solvating F minus, hydrogen from water. Let's say so solvation of F minus will be more. So more the solvation, greater will be the size of F minus in the polar protic solvent. So greater is the size of solvation, then chlorine will be solvated more as compared to bromine. So size of chlorine will be greater than bromine. So bromine after solvation will get greater size than iodine. So F minus has greater size than Cl has greater size than Br, then Br has greater size than I after solvation. So the mobility will be lesser here. So mobility will be lesser. So the nucleophilicity also will be lesser for F minus. So nucleophilicity will be in this order: Br minus, Cl minus, F minus. Nucleophilicity, that is directly proportional to mobility in solvent. Okay, let's see in the polar aprotic. Polar aprotic, what is happening? What do polar aprotic do? It solvate cations. Do not solvate anions. So polar aprotic always solvate the cations, do not solvate anions. So what is happening? We have HF, HCl, HBr and HI. So it is solvating H hydrogen. It is not solvating FCl, Br, I. So Fe, FCl minus, Br minus remains unaffected. So now we have to see the nucleophilicity, that is that will be greater for F minus. So because it has higher charge density, so charge density it has greater charge density, but it is not getting solvated. So nucleophilicity directly proportional to charge density. Okay, in the polar approach. Let's see in the non-polar. Let's come to non-polar solvent. Non-polar solvent. So what non-polar solvent do? Don't solvate cation and anions. It do not solvate cation, do not solvate anions. So if we have HF, HCl, HBr, HI, if we have this, so we have to see here bond length. So bond length of HI is greater than bond length of HBr. HBr has greater bond length than HCl. HCl has greater bond length than HF. So nucleophilicity is directly proportional to bond length. So it will be in this order. Okay. So I have discussed the nucleophilicity, basicity, and their correlations and the effects of solvent. Next we will discuss in the next lecture I will discuss the SN1 substitution reaction. In the substitution reaction we will basically do the nucleophilic substitution reaction. So thank you for watching. See you soon in the next lecture. Thank you.